So my name is Ran Issachar, and I'm working at the Geological Survey of Israel. First, I wish to thank Sasha for the opportunity to speak in the Rift and Rifted Margin seminar. And here I will introduce a work performed at Kiel University during a postdoc fellowship, together with Peter Haas, Nico Agustin, and Jörg Ebbing. In this study, we examined the development of the Afro-Arabian rift system and suggests that the mechanism of plume-induced rotation may provide a decisive force that triggered and enabled the initiation of the Afro-Arabian rift under acute rotational kinematics. Just a second. Okay. So this talk is a short summary of a long paper published recently, which includes a discussion and a review of the Afro-Arabian rift system and the mechanisms of plume-rift associations. And here I tried within a few minutes to summarize the main point, but I'm encourage the audience to read the actual publication. So I want to start with a question. The question is why Arabia is breaking up from Africa in the first place, or what triggered the disintegration of the Arabian continent from the African continent. Now, subduction is the first guess to derive the rifting, but here in this situation, subduction is ineligible because the Arabian continent is already colliding within the Eurasian plate since at least 18 million years. So, and in the Mediterranean, subduction still is ongoing. So, at least intuitively, the Arabian continent should slow down rather than accelerate or speed up. So, let's take this further and look at the acute rotational rifting that along the Red Sea and the Gulf of Aden. So this is the Illyrian pole of the Arabia rotating around Africa. So this is also another question: why that acute rotational rifting in this system? And another question is, or observation, is that the Afar plume sits in the junction of the rifting, of the Afro-Arabian rift. And this is a tomography model from Fechena et al. Showing the lithospheric, the upper mental relative velocities, and you can see the slow velocities beneath Afar. Okay, so the question also arises is, what is the role of Afar plume in this system? So we have three questions we want to address. Now, let us hypothesize that the Afar plume plays a significant role in the development of rifting and rotational kinematics in the Afro-Arabian rift system. Now, causal relationships between mantle plumes and rifting were way long suggested, as many examples in the geological record indicate a close spatial and temporal occurrence between the eruptions of flood basalts and continental breakup. Active mechanism was suggested by Jason Morgan already at 1971 to explain the widely observed spatiotemporal occurrence of mantle plumes and continental breakup. Following, Kevin Burrick and John DeVay, at their monumental paper at 1973, introduced the plume-generated triple junction mechanism, and discussed the Afar and other examples to support the active approach in which a plume-associated uplift and volcanism, here in A, weakens the lithosphere above the plume head and generate rifts from a triple junction within the plume region. And these are developed into developed rifting and oceanic spreading in the next stage. By this model, the rift arms nucleate and spread out from the plume area. This is a simplified cartoon to show the first stage of uplift and flood basalt volcanism in orange above the plume, and then rifting and oceanic spreading. So the temporal stages in the development of the Afro-Arabian rift seems to align with the active approach. As first, elevated topography. In this graph, we see the time scale, younging to the right, the elevation on the left side, and the opening rates of the different rift arms on the right side. So elevated topography in Ethiopia is estimated already since 40 million years before rifting, shortly, and this is the region of the elevated topography on the map. Following a massive flood basalt volcanism started at roughly 34 million years, and this is the orange polygons on the map. And the initiation of rifting in the Gulf of Aden at 30 million years, more or less, at the Red Sea and along the main Ethiopian rift. Here is the Gulf of Aden on the map, the Red Sea and the main Ethiopian rift follow this volcanism. They the rifts cross-cut and displacing the flood basalts area. So we still have flood basalts displaced by those rifts not today in Yemen, Somalia, and Nubia. Okay. However, we examine the architecture of the triple junction region from recent geophysical data and argue that this classical active view of plume-generated triple junction cannot explain the protracted development of the triple junction region. In this region, the development of the rifts at the Gulf of Aden and at the Red Sea, in which continental breakup accomplished and seafloor spreading achieved, meets the main Ethiopian rift, which is still under the stages of continental breakup. In this complex zone of interaction, at the Afar triangle, the three rift arms meets and interact. This is a very active area, including a lot of seismicity, volcanism, young flood basalts and active volcanoes, and we see the magnetic stripes of the Gulf of Aden and the Red Sea. While the main Ethiopian rift here on the south is still under continental breakup, of course. So what we do, we analyzed the margins of the rift in this intersection region from high-resolution DEM, and we find rough and irregular morphologies of the Gulf of Aden and the Red Sea arms, in contrast to a symmetric, continuous, and smooth morphology of the main Ethiopian rift arm. We use difference in Gaussian to map the rift margins, here shown in black on the map. And we find both in the Red Sea and the Gulf of Aden abrupt changes in orientation and drift width towards the triple junction. For example, here, and you see those graphs shows the rift width along the Red Sea and along the Gulf of Aden, and we see abrupt changes in rift width. In contrast to the main Ethiopian rift, where we see a smooth increase in rift width in a funnel shape towards the triple junction area. So this is a difference between those arms. Further, we use bathymetry, vertical gravity gradient, and Bouguer gravity anomalies to map the rift axis of these three different rift arms towards the triple junction area. And again, we see differences in the rift axis, the orientations and the style of the rift axis along the Red Sea and the Gulf of Aden. And what we see here, you see it more obviously in the Gulf of Aden, the rift axis is bent towards the interaction area, towards Afar. We see it in the bathymetry and also in the vertical gravity gradient. And also this phenomenon occurs in the Red Sea. While in the bathymetry, we don't see a pronunciation of the rift axis in the Red Sea, but in the vertical gravity gradient, we see the typical signature of the rift axis bent towards the shoreline.
And you're at 11 minutes now.
Okay. Moreover, we see fossilized, arguably abundant rift axes that connected along the marine connection between those basins that connected those two rift arms. In contrast, along the main Ethiopian rift, we see a smooth, non-changing orientation rift valley that goes all the way to the discontinuity, the Tendahogoba discontinuity in Afar. Okay. Now, we discussed the architecture of the triple junction here, and we say that these morphologies suggest a recent tectonic reorganization of the triple junction region by a northward propagation of the youngest main Ethiopian rift arm towards the mature Gulf of Aden and Red Sea arms, including diffuse deformation, microplate tectonics of the Danakil and Ali Sabich microplates, the abandon of the former tectonic connection between the Red Sea and the Gulf of Aden. And these insights implied that the triple junction was the last feature to develop in the system. When all three rift arms were already developed, and the breakup between Africa and Arabia had already accomplished. Our interpretation also agrees with structural geochronology, showing extension in the northern main Ethiopian rift commenced only about 11 million years before today, and this is more than 20 million years after flood basalt's eruption. Hence, the classic model of a plume-generated triple junction cannot explain the architecture of the triple junction in the Afro-Arabian rift, as the rift arms did not spread from the plume region. The formation of the triple junction occurred 20 million years after flood basalt magmatism by a northward propagation of the main Ethiopian rift. Nevertheless, the mechanism of plume-induced rotation can explain the protracted development of the triple junction region. Plume-induced plate rotation was suggested recently by Joe Hinsbergen and Bernard Steinberger and co-authors to explain the acceleration and rotation of the Indian plate following the arrival of the Morondova plume, shown here. Using detailed reconstructions and torque balance modeling, they suggest that the drag forces beneath the lithosphere induced by the plume drastically changed the tectonic framework, triggering the formation of new plate boundaries. In the case of the Afro-Arabian rift, mental flow predictions by Facena et al. Shown here show deviation of the upper mental velocities in association with upwelling convections below Afar. By adopting the plume-induced plate rotation to the Afro-Arabian rift system, settles the observation that the formation of the rift did not nucleate it from the plume region. Instead, the plume-induced horizontal forces that were added to the far-field forces and changed the tectonic framework caused Arabia to accelerate and derive new divergent boundaries with acute rotational component. Plume-induced rotation also aligns with the delayed development of the main Ethiopian rift, which started around 50 million years after flood basalts, and with the late onset of the triple junction, which occurred around 20 million years after flood basalt, as these are controlled by the slower kinematics of the Somalian plate rather than the gravitational forces exerted by the plume head. So in summary, we say that the classic active plume rift approach not align with the protracted development of the Afro-Arabian rift. And we say that plume-induced plate rotation aligns with the protracted development of the Afro-Arabian rift and may explain the acute rotational rifting here. However, to better validate this argument, a modeling component would be required. I just encourage the listeners to propose or think of a modeling to strengthen the proposition that afar plume derived rotational rifting at the Afro-Arabian rift and forward our understanding of the geodynamic role of mantle plumes. And this cartoon illustrates the mechanism that the plume pushes the continent from a point here in afar and causing the rotational rifting. That's it for me. Thank you for listening.
Thanks a lot, Ran. There's time for 1 or 2 questions. So if you have a question, please raise your hand or put them in the chat, depending on how you want them answered. Derek, go ahead, please.
Thanks, Ran. Nice talk. Thanks very much. So I was just for the sort of dramatic rotation of the plate motion from Arabia to Anatolia, is the interpretation that's caused by the plume, or is there some other mechanism in the north that's causing this sort of dramatic rotation to the west?
Yes, so of course there are far-field forces, and there is the kinematics of the plate. Maybe I can go back to the first slide that shows this rotation. I'm sorry. Yeah, here. Let's look at it. So of course the far-field forces are also adding up. But what we say is that if we add the plume push, then it can settle this entire rotational kinematics. It can be an addition to the far field,
Okay.
But as to my best knowledge, there is no discussion at the literature, or at least no suggestions why why Arabia rifted from Africa in the first place. And the mental convections proposed by Facciana et al. Suggesting that a convection cells of upwelling from the afar area, horizontal flow northward, and downwelling in the, again, area is deriving this rotational rifting. But they did not consider the plume push forces that cause rotation also. But I think that we have to consider the mental in order to explain what we see, the kinematics of the crust. This is what I think.